Good day again, everybody, and welcome to Theorem Physics. Today we look at logic gates, some tips and misconceptions. We begin with equivalent circuits. In our first example, we are asked to explain and draw a truth table for an exclusive OR gate. Before we begin, let's recall that logic gates use binary digits, specifically 0 and 1, where a 0 is considered to be a low value, whereas a 1 is considered to be a high value, or high output or input. But what is the difference between an OR gate and an exclusive OR gate? Well, an OR gate allows or permits the output to be 1 or high once there is a high input, meaning that any one of the inputs having a value of 1 means that in our truth table we are also going to get a binary value of 1 as well. However, the same condition is not used or affiliated to an exclusive OR gate. An exclusive OR gate has one stipulation where our two inputs are identical, our output is low. This means that an exclusive OR gate is fundamentally an OR gate exclusive of the condition where our two inputs are the same. In our second example, we are asked to create an equivalent circuit for the one given in the diagram. Here we can actually label our inputs from the two original inputs given, which means fundamentally our diagram, even though we have three logic gates, we have two inputs, A and B. What does that tell us? When there are two inputs, the number of rows can be calculated by the value of 2 to the power of n, where n represents the number of inputs. So if we only have two inputs, then our number of rows will be 2 raised to the power of 2, which gives us 4 rows. If we only have 4 rows and 2 inputs, then it would make sense that our number of inputs and the possible combinations can be stated as follows. The output C can be determined from a NAND gate using two inputs A and B. It would be interesting to note that a NAND gate is considered to be a not AND gate, the outputs of which are opposite to an AND gate. So while an AND gate requires two inputs to be high for an output to also be high, the NAND gate does the opposite. Also, output D comes from the same two inputs A and B as it passes through an OR gate, the results of which are also shown. And finally, output E can be determined from outputs C and D, which now becomes the inputs for the AND gate at the very end. The results are synonymous to an XOR gate. Negated inputs versus negated outputs. Here we have two diagrams which we are asked to find out if they are the same. In our first diagram, which we can call part 1, we are given a NAND gate connected to two NOT gates, the inputs of which are connected to two NOT gates, whereas the second diagram gives us an AND gate connected to a single NOT gate, which can be represented or shortened as follows. When input A passes through a NOT gate, we can call that A bar, also known as NOT A. The same can be applied to input B. Our truth table will therefore have 5 columns: A, B, NOT A, NOT B, and of course our final output C. Once again, because we only have two inputs, we have 4 rows, the inputs of which for A and B are given also as follows. The NOT gate gives an opposite output as any input that passes through it, so A bar gives the opposite output of A. Similarly, B bar gives the opposite output of B. When both A bar and B bar passes through an AND gate or feeds into an AND gate, we get our output C, where for an AND gate we need two inputs that are high for our output to also be high. In our second diagram, we can call the output from our AND gate R. Once again, since we only have two inputs, A and B, our number of rows remain the same, which of course would be 4 rows. Once again, A and B are fed into an AND gate to give us output R, but is then fed into a NOT gate, which gives us our final output C. The values of C are quite the opposite to R, giving us therefore 1, 1, 1, 0. It's also called the NOT values of R. In comparison, we can see from our truth tables that both diagrams do not yield the same results, so we can therefore conclude that they are not the same. In other words, when the two inputs of a gate are NOTed, they do not yield the same results as having the output of that same gate being NOTed or negated. The same condition applies for an OR gate that can be used in a similar setup. Same signal input. Such gates have one shared input. Since there's only one input, the number of rows should be given as 2 to the power of n, which is of course 2 rows. This is quite similar to the input of a NOT gate. For input 0, it means that both legs of the input parts of the circuit also indicate a 0 or low input. However, we can use a NAND gate or NAND truth table to remind ourselves of what we expect to obtain using a NAND symbol logic gate. Here we can see that for a NAND gate, 2 low inputs gives us a high output. It would therefore make sense for B, our output for the shared input, to also be high or 1. We look at the last row for our NAND truth table as well, where if 2 inputs are high, then our output will be low. What do you think would happen if another such gate feeds into an equivalent gate as shown? A sequence that can be seen on the screen. To answer that question, when one gate as such follows another, they tend to cancel each other, meaning the effect of both of them are null and void. So if we consider the circuit given below, where we have 10 NAND gates, we can pair our gates that cancel. We can therefore pair the gates that are closest to each other with the same shared input. Can we therefore simplify this circuit? Well, let's see. Yes, we can. So instead of using 10 gates, we instead end up with 4 NAND gates. Thank you for watching, and feel free to ask any questions in the comments below. Like and subscribe and follow us for more videos.